Uh, Hi, my name's Duncan Mays. Many of you know me, and I'd like to present to you my work on benchmarking DCP workers for runtime prediction. So the goal of this study is to be able to predict the runtime of a certain slice on a certain worker. And the way we're going to do that is we're going to run benchmarks on the workers to determine their compute characteristics, and then we're going to develop some kind of analytic that operates on those benchmarking scores and can give a prediction of the runtime of a certain program. Now, this is an important component in a scheduling system. If you'll imagine the problem of assigning a set of tasks to a set of workers with the goal of minimizing the completion time of those tasks, if we know the amount of time each task takes on each worker, then this is a linear programming problem and it can be solved with fairly well-known methods. And so after runtime prediction, the task of distributed scheduling becomes a lot easier. There are also two questions which we hope this study will answer. Firstly, how accurately can we predict runtimes in the first place? Even with the best benchmarks and the best analytics, there's still going to be noise in a worker's compute characteristics due to things like resource contention. And so we need to understand how accurately we can predict these things. Secondly, are CPU characteristics one-dimensional? It could be the case that the fastest CPU always gets the job done fastest, but it could also be the case that certain JavaScript runtimes are better at certain operations than other JavaScript runtimes. Maybe the ARM version of SpiderMonkey is really good at matrix multiplication, for instance. And so to be very clear about the problem at hand, we want to develop a model that can operate on a worker's benchmarking scores and give a prediction of the amount of time a certain task will take if it is run on that worker. The way we're going to do this is we're going to deploy a DCP job that runs several benchmarks and sampled programs on workers, and then each worker will report back to the client its score on each benchmark as well as the amount of time it took to complete each sample program. And the client will record this and put it into a data set. All of the benchmarks we've run only focus on CPU characteristics. We did not benchmark GPU characteristics or the input-output bandwidths of a particular worker. And we ran 8 benchmarks total, 5 of which were math-based, that being the addition, subtraction, multiplication, division, and the modulo operation. We also benchmarked the worker's ability to iterate over a loop, the worker's ability to access elements in an array at random, and the worker's ability to recursively call a function. So all benchmarks broadly followed the same skeleton code. You can see the while loop here. It runs for a certain amount of time, and in this case 3 seconds, and it counts the number of times that it can call a certain function f. Now for math-based benchmarks, this function f iterated over 2 random lists and then performed some operation on the elements of the list, and that operation is the operation that the benchmark is named after, so the addition operation adds them, the multiplication one multiplies them. That's easy to figure out. The rate over loop benchmark measured the number of iterations over a loop that the worker could achieve in 3 seconds. And so f just iterated over an empty loop. In array access, f accessed random indexes in a target array, and it's important that the indices that it accesses are set randomly, and this is to prevent the CPU from caching the result. And recursive depth, f recursively called itself up to a certain depth limit, and this is to measure the amount of time that the CPU takes to switch contexts and move into a different function call. So we ran 3 sample programs, and again, we only focused on CPU characteristics. None of the sample programs accessed to the GPU or communicated in any way. Sort was a sample program that used quick sort on a randomly set list of 10,000 elements 1,000 times. Prime searched for primes up to 3 million, and homography transformed an oblique image of a triangle to be straight on 3 million times. So homography is an image transformation operation. So we've conducted this study over a course of about a week in the early summer, And in this study, we surveyed 1,200 workers, and around that time, only around 1,000 workers were active. So it's safe to say that we surveyed most of the workers that are active on DCP. Now, in the following data exploration, we also considered the inverse of the runtimes of the sampled programs. This is because the runtimes of the sample programs should have an inverse relation with the benchmarks. And so the inverse of the runtime should have a linear relation with the benchmarks, which means that it'll correlate more strongly because correlation math only works on linear relations. It doesn't work on inverse relations. So here's the correlation matrix of all the benchmarks, the runtimes of all the sample programs, and the inverses of the runtimes of the sample programs. And there's three pieces of information that we can draw from this. Firstly, if you look at the top left of this square, we can see that all the math benchmarks correlate very strongly with one another, and much more strongly than the other benchmarks correlate with each other. Secondly, if we look at this block on the correlation matrix, we can see that the inverses of the runtimes of the sample programs correlate at different levels with the different benchmarks. For instance, the inverse of the prime search program has no relation with the recursive depth benchmark because of this square here. Thirdly, if we look at this yellow block in the middle of that blue cross, we can see that the runtimes of some of the sample programs don't correlate very strongly. For instance, the runtimes of the sort program and the runtimes of the prime search program don't correlate at all, which is pretty interesting. So because all of the math-based benchmarks had a very high level of correlation, we're only going to consider one of them. We're only going to consider the addition benchmark. And so in the following analytics, we're only going to look at 4 benchmarks, 4 out of the 8, that being addition, array access, rate over loop, and recursive depth. So again, before we start talking about our analytics, we need to talk about the metrics of success that we're using. So we're going to assess our methods using histograms of their percent error. So you can see examples of those at the bottom of the screen. In these plots, the x-axis represents the percentile that a certain data point falls in, and the y-axis represents the number of data points that fall into each percentile. So the more left skewed the plot, the lower its mean is, the more desirable the solution. So for instance, the plot on the left corresponds to a better predictive method than the plot on the right because it's more left skewed. The first method we used was to simply use a line of best fit. And this operated on the average of all the benchmarking scores. So this method considered that the CPU characteristics was one-dimensional, and it also assumed a linear relation. And we find that this only worked partially effectively. If we look at the plot on the left for homography, we can find that we get a mean error of around 20% with this prediction method. So that means that on average, the prediction of this method will be accurate to within 20%. But we also see that there are a fair number of predictions that are over 100% off, which means that this method predicted twice what the actual runtime was, which is not a desirable solution. On the prime search program, we can see that we again predicted within an accuracy of 20%, but on the sort program, we had an error of 30%, and quite a few of the predictions that this method made were over 100%, had over 100% error, which is not a very good solution at all. The second method we used, again, considered CPU characteristics to be one-dimensional and used an average of the benchmarks. But the line of best fit we did was a order 3 polynomial. So it could capture curves in the data set, as you can see in this plot. And we don't get a big benefit to performance doing this. With homography and prime search, we get a benefit of around 5%, but we still get lots of predictions that are over 100% off, and the sort sample program still cannot be predicted with a lot of accuracy. The next method that we used was a neural net. And this considered the benchmarks independently. So it had 4 inputs for each benchmark. It had a hidden layer of 100 neurons activated with ReLU, and we trained this over 100 epochs across our data set of 1,200 data points with Atom to estimate the runtime. And we get a slightly better performance on the sort sample program. Before, with the line of best fit methods, we had an error rate of 40%, whereas now we have an error rate of 30%. But the prime search and homography sample programs are not much more accurate using this method than the other methods. And notably, we get a lot less estimates over 100% error, but we still get some. So that's an important point.
Do you think that's because of Q-sort degeneracy in some cases?
I'm not sure what Q-sort degeneracy is.
It's like in worst case, it could be O(n) squared instead of O(n) log n.
Oh, for the sort program? Well, yes. So if I remember properly, quicksort doesn't work very well when the array is already kind of in order, right? And the array is randomly set, so there is a possibility in some cases that it could be out of order like this. Mm-hmm. So that's an interesting point. Maybe we should have used a better sample program that runs in a determinate amount of time. Didn't think of that. And so to answer the question, how accurately can we predict runtimes? It seems to depend a lot on the program we're trying to predict, but we've found it can be bounded above by 30%. And to answer the questions of are CPU characteristics one-dimensional, we don't get a lot of benefit from considering more than one benchmark. And so it's unlikely that this is the case. The next steps in this research are as follows. In real-world settings, we have very limited data on workers' benchmarks and the runtimes of slices. In the context of DCP, to be useful, we would need our analytics to work after only a handful of slices have returned. And so we need to develop predictive methods that can operate on very little data. Secondly, we need to widen the scope of this study to include GPU and communication workloads, because a lot of work that people do on grid computing systems use GPU and communication. And thirdly, the benchmarks and sample programs were invented for the purposes of this study. We should have used benchmarks and programs that are more widespread in grid computing research and are more representative of the workloads that DCP works on. That's the end of my presentation. Thank you for your time.
Can I jump in with questions?
Certainly.
Duncan, you've been reading my mind, which is not surprising given you spent a summer here a couple of years ago. This is absolutely topical for me these days because we're finally starting to get into the point where we're becoming interested in relative workload performance. And in particular, I think you've sort of hit one of the nails on the head, which is that I need to get an idea of what my workload is going to perform like on a wide set of workers given only a very small amount of data. Right now, we're actually only using 2 slices of the work to generate our prediction for our initial set of slices to be scheduled for the first set of tasks. So I can't wait to see what else you learn. I actually had a couple of quick questions about your benchmarks.
Sure.
Do all of them have that pattern in the program where they iterate for date.now?
Yes.
Yeah. Have you considered that you're actually benchmarking the performance of the utime system call when you do that? So that's going to add a static overhead to every pass of that particular loop that is going to be operating system and machine dependent. And you might be able to correct for that by essentially rerunning it for a loop counter that's similar to the loop counter that you have in there. And or correcting for it based on the actual number of iterations that you've got on the go there. So, for example, if you've got a high number of iterations in your benchmark, then you know that you've done an awful lot of date.nows, but if you only got a few, you haven't done as many. Also, there's also the possibility that your system clock has been skewed during a reasonably long benchmark run due to the effects of NTP. That shouldn't be a big deal, but you can correct for that easily enough by using performance.now in JavaScript, which gives you a monotonic clock. And I just wanted to check in too with respect to your array access benchmark. Were you using JavaScript arrays? And if so, approximately how large were they?
I was using JavaScript array. I think it was about 10,000 indices.
Okay, 10K is pretty low, so you're probably not running into the issue that I was wondering about. And that issue is that in a typical JavaScript virtual machine, I don't know what the limit is today, but it used to be something on the order of 20K. What happens is if you get a lot of array elements in an array, the engine will internally de-optimize it into a bare object and then do object property lookup on your array properties, which completely messes your performance and the way and like your cache locality, your locality reference and all that stuff. And that also happens if you're using if you're declaring your arrays with a lot of holes. That can happen as well. So when you're warming up for your benchmarks, it's if you want to do another pass of these, you might want to warm them up by populating the data. But I was also going to suggest using byte arrays rather than arrays for what you're trying to measure, because the internal storage of a typed array type in JavaScript is essentially an object that has an internal reference to a C array of that type, whereas a JavaScript array essentially is an object with an internal reference to an array of JS vals, and JS vals themselves are then tagged variant data types, kind of like Lisp types. They actually use NAND tagging in most engines today. So there's essentially a double indirection every time you're doing a lookup there, and you can wind up measuring array lookup a bit more than you might want to for the benchmark that you're measuring there. But what I wanted to share with you and to ask you if you had any thoughts, and maybe to ask you to have some thoughts in the future about this, is it would be really cool in DCP if we could say, hey, I've got this benchmark and it runs like this on this machine, and we know these characteristics about it. Now we've just run this workload on our estimation stuff, and we're going to use that to schedule some stuff out there in the world. But what would be really interesting is if there was a way to then use the actual active workload and potentially its performance against its predicted behavior to sort of feed back into the scheduler to give us better information for the next round of slices that get sent out for a given job. Because one of the problems that I have in DCP, in fact, is not just that it's difficult for me to benchmark workers at times, but also it would be really interesting if we could get to the point someday where we use work to benchmark workers. Which is starting to get pretty meta, but it would be very efficient if we could ever pull it off.
Yeah, that would be really cool.
So that's it for me.
I'm going to stop sharing my screen. Any other questions?
Thank you so much, Les, for the feedback and for the questions and comments. And thank you, Paul and Dan as well. Thank you so much. So any more questions or comments?
Oh, I just had something in the back of my mind, which was something that different processors really have different behavior in is how will they deal with branch misprediction. I mean, the reasoning being that some processors have much larger pipelines of instructions, and a misprediction means they flush the pipeline, they do it all over again. And I think that's hit by quicksort but it might be swamped by memory latency. I don't know. It's just something I was thinking about.
Actually, kind of in the same vein, and this might be interesting to measure, Duncan, if you decide to get into more measurements. The same thing will happen in JavaScript with the JIT. JavaScript's got a really unique set of problems. And these problems actually vary from implementation to implementation. But they're all caused by the same thing, which is that all the types in JavaScript are one type effectively, which is a variant type. And one of the interesting that happens is during the JIT is that the JIT compiler will actually produce compiled fragments for different combinations of potential and predicted type mutations. And then it will throw them out as it sees they don't get used. And then it will regenerate them if they do. And it might be interesting to see benchmarks that actually discuss or explore some of these nooks and crannies of JavaScript, because real-world JavaScript programs tend to do these things. And if you're curious about the JIT strategy that I'm talking about, the paper you want to read is by Andreas Gall at CMU. It would have been published around 2007 or so. And his paper actually wound up being the model for the first JIT that was implemented in Mozilla SpiderMonkey, which is the reference implementation for JavaScript.
That's really interesting. Sorry, how do you spell this guy's name? Andreas Gall?
Andreas, so Andreas space Gal. And I'm not sure where he's working these days, but he was at Mozilla, and before that he was at CMU.
Okay, cool.
Any more questions? Okay. Thank you so much. Thank you for your feedback, and thank you for letting us know about the updated version of DCP. We're so excited. So,
and thank you for sharing these ideas. I love these meetings.
It was fun.
Thank you. Okay. See you next time.
Bye-bye.
Have a wonderful day.
Bye-bye.
Thank you, everyone. Bye-bye.
Thanks, everyone. Bye-bye.